Thank you so much, Professor. Thanks for agreeing to do this interview. So would you introduce yourself and tell us more about your educational background? I mean, when and where did you go to high school?
Yeah, thank you very much for the invitation for this interview. So my name is Mattias Edén. I'm professor in physical chemistry at Stockholm University, I've been a professor since about, 2013. I was born in a suburb around 20 kilometers northwest from Stockholm city center. And that's actually where I've been living pretty much my entire life, not at the same place. But basically, I've been living here for my entire life, except for 2 years postdoc and 1 year sabbatical. Um, and So this place is called Jakobsberg. I did my primary and secondary school here. Then I continued it doing studies in chemistry at Stockholm University. I think I started, it was 91, I think. And also, except for this postdoctoral stays, I've also been at Stockholm University actually since pretty much 1991. So I have since long been interested in chemistry. So I continued doing a PhD under the supervision of Professor Malcolm Levitt. He was basically faculty at Stockholm University, from the early 90s for about a 10 years period. So that basically overlapped with, I started my PhD in 1994, and then I finished, I think it was in 99. So that's pretty much sort of my educational background.
In high school or during your undergrad, what was your favorite subject?
I think that during the primary school, I think I was pretty much, I didn't have any obviously favorite subjects. I was pretty much interested in most of the things, particularly sort of Swedish language. I also liked mathematics. But this chemistry interest, I got even well before you had any sort of chemistry education at school. They started basically when I was about 9 or 10 years old. This was basically in the very early 80s. It was very different times then. I mean, you could basically buy these kind of hobby chemistry kits, which I did when I was 9, and I got very interested in that. So I started having basically in the house, there was a room where I had a small space for basically a lab, which I was doing starting pretty much when I was 9 and doing for a few years. Like I said, it was very different times back then, because you could, in Sweden, the drugstores were basically like sort of state-owned, but you could pretty much get almost a lot of chemicals there, which are totally banned since a long time ago. There was even kind of chemical companies. I mean, I could buy basically concentrated mineral acids. I was doing it for the interest, so to say, but I did fairly crazy things then. So this is basically how my interest in chemistry started. And I didn't have any formal chemistry until basically the start of secondary school. But from when I was quite young, it was definitely, I was determined somehow to be a chemist.
Yeah, it's interesting that you could buy acid, right? You mentioned concentrated acid as a kid.
Yeah.
Yeah, but is it possible nowadays, or it's you said?
No way. I mean, I think that Sweden is pretty much, I guess, very similar to in Canada. I mean,
Yeah.
even if you look at university level, there are many chemicals that you can of course buy, but you have to give sort of reasons for buying them, because they are somehow dangerous in one way or the other. And But back then it was very different times. I remember there was at the library, I was sort of borrowing and re-borrowing a book which was written probably sometimes during the 60s. And it contained fairly advanced experiments. I mean, like I said, I never did this for somehow making bombs or stuff like that. It was more for the general chemistry. But still, you have to consider you're a kid. And I mean, I was doing things like nitroglycerin when I was 11 and 12. And I mean, that's something which, of course, is totally outrageous in many ways. Now somehow I'm not coming from an academic background, so my sort of parents were supporting me in all this, so to say, but I don't think they somehow realized many of the things, how dangerous things were. I mean, I've been exposed to pretty much any sort of toxic gas, from chlorine to bromine, for instance. In this book I was referring to, there was basically some descriptions how to make bromine from salt water or seawater.
Yeah, so I'm happy that nothing bad happened to you.
Yeah, I mean, I probably had the guardian angel, but everything I was exposed to concerned the cancerogenic stuff. I mean, I was, for instance, making benzene, which you can do if you just use the sort of sodium benzoate, which you can buy, it's a preservative, so you can buy it basically that you can still buy at any store. You mix it with, let's say, some alkaline like calcium hydroxide. If you heat it up, you're going to generate benzene. And then the idea is, of course, to cool it down and get the benzene liquid. But I mean, I can still remember how that smelled. And that is one of the things that since quite long now has been identified as being extremely cancerogenic.
Yeah, you mentioned several times that the things have changed within the past few years. I mean, uh, I assume that kids they are not allowed to do all these things by themselves. It's interesting that when I was talking to Mark Conradi, he also talked about his experience. He was working in a surplus shop, in a radio shop, and how it was helpful and beneficial for him later on when he started doing his career, hands-on. uh, I mean, how comfortable he was working in a lab making probes. And also I remember that Professor Rod Vasilishin was telling something like this, that he was working, uh, doing these lab things in the basement when he was a kid. So it's interesting that you also have the same experience. So how do you see this change affect the quality of the quality of students? I don't know how I should put it in. I mean, how do you see this lack of experience has affected the students you see nowadays? I hope I asked the question clearly.
I'm not sure if I got it. You're referring to not having the possibilities to somehow do have some of hobby chemistry lab at home. Is that what you're referring to?
Something like that. So do you see, do you think this is something helpful, beneficial, really, or everyone should?
I don't think it has changed much, because I mean, what I was doing was for sure not anything that was somehow common to do. I don't know anybody else who had a hobby chemistry lab. So probably there were a few, and they, like me, probably got very interested in chemistry, and it somehow helped them later on. But I don't think that the difference is, if you take nowadays students. I think the other problems that because I can still see myself from my first years of in the early 90s to teach as a TA in university courses in chemistry, and later then on as a lecturer now for many years, that you can see that the knowledge of the students is rapidly dropping, particularly concerning mathematics. And that's basically a consequence of quite, I would say, detrimental changes in the kind of curricula at the secondary and particularly high school levels.
Actually, the reason that you chose chemistry was because of your experience with these toolkits that you had, right? Chemistry kits that you had,
Yeah.
right? So then how you got to know your supervisor, Professor Malcolm Levitt? How did you know him, and what did you do for your projects during your PhD?
Yeah. So when I was still studying chemistry at university, I was kind of quite open to most of it. I mean, my favorite subject of physical chemistry started materializing probably throughout my second half of my bachelor studies. So we had then a course in it was basically mainly spectroscopy and some sort of, I wouldn't call it quantum mechanics, but the very sort of simplified sort of quantum mechanics type of thing. And Malcolm was teaching part of that course. So that's when I sort of met him the first time. And then something like a year later, I was determined to continue with physical chemistry, and then I had, well, some offers to basically do like what you would say the kind of undergraduate diploma work. Diploma work it was it would be called in Germany, for instance. And I picked up Malcolm's project there. I mean, up to that point, I wasn't really knowing that much about NMR. This is something, an interest that's sort of rather started growing. So I did this diploma work, and then later on I continued doing PhD.
Okay, and what did you do during your PhD?
Actually, quite a lot of different things. Um, um, I would say that probably for most of my PhD, I was actually spending programming, basically to simulate solid state NMR experiments. I mean, this was basically a few years before Simpson came, and nowadays everything is totally different. You have basically open and free software to do simulations. I was basically building up not nearly as complete or advanced as Simpson, but I was basically writing my own software, which I think was quite common in most of the groups doing method development, because that is basically the core of what Malcolm Levitt's research group then. It was basically mainly about recoupling techniques, dipolar recoupling techniques, which I was also as sort of having as one sort of side projects. But I started basically doing numerical simulations that amounted in basically an algorithm called compute, which I think also you can find in pretty much all of these open softwares like Simpson, the spin evolution. I don't know if that is active anymore, but so I was doing a lot of programming to simulate NMR experiments. Then if you're looking at my PhD thesis, the title is quite a general. It was something, what was it now? Solid state NMR on multiple spin systems. So as part of my thesis, I basically had two papers which only related to simulations. I also worked on somehow sampling crystal orientations for doing efficient powder averaging. Then I was also, like I said, also involved in the work of the symmetry-based pulse sequences, which starting with the so-called C7 that Malcolm did in collaboration with Nils Nielsen in Aarhus. And I was doing some contributions there. None of those papers were actually included in my thesis. So to say, the second half of my thesis concerned how to measure torsional angles in, let's say, peptides. And that I was also part of. So I was part of several different projects in Malcolm's group. Then when everything needed to be wrapped up, well, it was with this very general title of solid state NMR on multiple spin systems.
Mm-hmm. Interesting. How did you learn programming? I mean, was there a course, or you just liked it and you tried to learn it independently?
I think that in part I got some help from Young Lee. He was a postdoc in Malcolm's group. He was doing PhD with Alex Pines in Berkeley. And he generally had, up to the point when I started learning, he basically had this kind of rule in the group that he knew programming, so he was doing simulations basically on different NMR experiments, particularly dipolar recoupling experiments. So he helped me to get started. But I basically started pretty much. I had during my high school studies, I was having Pascal. I mean, basically like in the education. And so I started basically learning C, and it's basically from there. So you can say that I'm in a sense self-taught with some help initially from another postdoc in the group.
So interesting. The, are you involved in any sort of experiment or method development nowadays? I mean, or just you? I mean, usually professors, they don't do experiments. They don't have the time. This is why they hire students. So are you involved in any experiments or simulations or method developments?
If you're
By
talking
yourself, I mean, you.
yeah, you mean in hands-on?
Yeah, exactly.
Well, basically no. Concerning experiments, I'm usually supervising them, and
Yeah.
depending on the knowledge of the person, like I had a few very talented PhD students and also postdocs who were basically running this themselves. To be honest with you, at this point now, I actually couldn't run any more experiments myself because.
Yeah, I have heard it from different professors. Yeah, because the technology, it's evolved, right?
It's basically like this. We had, when I was doing PhD, we actually had an old Bruker MSL, which I was doing experiments on. It's very different from the current Bruker. Then during my PhD, Malcolm got basically funding. At the time, we had a 200 magnet. It was a Bruker MSL. That magnet was kept, but we then got a new 9.4 Tesla magnet together with, at the time, was called Chemagnetics. It was a Japanese company that had really excellent, let's say, performance concerning to set phases and amplitudes. I mean, basically, in the middle of the 90s, they had capabilities that Bruker didn't get until probably a decade later or so. So the point is that I was trained on this chemagnetics equipment. During my postdoc with Professor Lucio Frydman, everything was basically home built. So nowadays we have since more than 10 years basically Bruker equipment. So what I mean that I wouldn't, when I say I wouldn't be able to do the experiments myself, is that I can easily supervise experiments. I know what to do, but I'm actually not trained on the sort of newer Bruker equipment. I mean, I can do sort of understand the essentials of the pulse programming and so on. But concerning numerical simulations, I was basically doing that myself up to well, it's probably more than 10 years ago. But still, I was doing it beyond when I was at the professor level. Nowadays, I'm not involved in any of that anymore.
Yeah, it makes sense. So tell us more about the challenges you faced during your PhD program. I mean, when you were doing your experiments, simulations, the whole project, the whole program. I mean, the PhD. Uh, Tell us more about the challenges.
Yeah, I think, yeah, sure. I think there were many challenges. To start with, Malcolm's research is somehow well known to be top class. So it's very often not super safe projects, but they are somehow potentially very rewarding. So, like I said, I was involved in a lot of things. A lot of things somehow I was struggling with, and I think that in the very beginning of my PhD, I somehow realized, because I'm not known to be the most patient person. I'm usually systematic and careful, but I had, which I could identify back then. I mean, I was in my mid-20s, that I tended to rush things. And then you realize after a while, for instance, if you're writing a code or something, that you made a big mistake, and then you have wasted 1 week or even more just on rubbish simply because you made this mistake. So that from that time, I somehow got, I really started to be really somehow careful at every step to avoid these kind of things. And I think that's something I kept since then, which has really helped me. But like I said, I was involved in many different type of projects, and I think that was a kind of blessing to be in that situation. Very often I was complaining to Malcolm when things didn't go well, but I think this is something like, you mature over the years, and you somehow learn that really, if you want to do really somehow challenging or potentially very rewarding research, you have to take some sort of risks.
Then you spent a couple of years in Professor Frydman's research group as a postdoc. So how did it go? Tell us more about it, please. And what was the project over there, or projects?
So basically, during my PhD, even if those papers were somehow not really included in my PhD thesis, I was doing basically method development, mainly dipole couplings technique to measure distances. All those were basically implemented on kind of very simple model system. Usually, I mean, it was carbon-13 distances often, so you used carbon-13 labeled amino acids, which you can buy. So the reason why I wanted to do a postdoc with Lucio Frydman was to learn about quadrupolar nuclei. Just a few years earlier, he had somehow invented this triple quantum or multiple quantum magic angle spin in the MQMES, which totally revolutionized the research on quadrupolar nuclei. So I wanted to learn more about quadrupolar nuclei. What I then somehow ended up with doing was some sort of hybrid, still using dipolar couplings, but now trying to do homonuclear dipolar interactions between quadrupolar nuclei, like boron 11, or I think some of the stuff we were looking at was even lithium. So that's basically what I was working on there. I'm usually referring to that time that I started in Chicago and I ended up in Israel. I was doing a 2 years postdoc, and during 2001, that was located in Chicago, where I also met the postdocs Rob Shurko and Chris Grant. I'm not sure really if Chris is still in the NMR business. He used to be a staff scientist at Stanopella's lab for a long time, but I'm not sure if he's involved in NMR anymore. I met those guys. We had a great time. Then I got to know later that Lucy had accepted a position at the Weizmann Institute in Israel. So in the beginning of let me see. No, wait. In Chicago, I was doing the year 2000. In the beginning of 2001, I was moving to Israel.
As a professor, you didn't start with glass science, right away. Is that true?
Yeah. No, I would say that most people who's doing somehow glasses in general, they usually have a background or either a PhD or postdoc in glasses. I had absolutely no connection to any person doing sort of work on glasses. So I basically, like I said, during my PhD, I'm coming from a basically pure methods development background, which basically was also staying throughout my postdoc. The difference was that then I also did a little bit work on, let's say, I wouldn't call it inorganic materials, because it was usually quite simple inorganic salts and stuff like that. But then I knew that I had to do something after my postdoc. And the options at the time was basically to get to apply to the Swedish Research Council for, you could have a 4-year position, which was basically, it would, the title would translate into English as assistant professor. So it's basically, it's a 4-year time limited position. So it's basically an assistant professor without the option of tenure. So you know that you have to find something else there. When I then was moving back, so I applied to the Swedish Research Council, and then I applied for a project basically also involving methods development, dipolar interactions, like this kind of stuff I was doing during my postdoc, but to apply it for glasses. And the reason for that was mainly for somehow, I know that it's a relatively easy way to sell, given that glasses are amorphous, so NMR is extremely powerful for exactly those type of systems. But you see, it was something that I remember that in the spring of 2001, when I basically got to Israel, I would say that that was a very somehow time where I felt a lot of pressure, because I knew that I need in a few months to basically come up with a new project. And I somehow managed to do it. I wrote the application and it got funded. So then I got to know basically during the end of 2001, during the end of my postdoc, that I got this position, which then would mean that I would get back to Stockholm University, because at the time, solid state NMR was basically, I think you could find it in, besides Stockholm University, in 2 other places. One is up north in Luleå, and that is also direct consequence of Malcolm's stay in Sweden for 10 years, because one of his PhD students, Olegan Sutkin, he was a senior PhD student to me. He got the lecture position up there. So I could go back to Stockholm University, and that's how it somehow started. But I'm totally self-learned, so to say, concerning glasses and NMR on glasses, so to say.
Okay, interesting. So, what was the first project you did in glasses?
Well, my application was basically, besides method development, the applications would be target and borophosphate glasses, which I guess you have worked with a bit.
Yeah.
The funny thing is that I still have done very little work on borophosphate glasses since, well, over the past 25 years. So when I got back to Stockholm, there was a coincidence, because one of the things I was hoping at was that I could get some sort of internal collaborations, because back at the time, our department was basically divided in 3 divisions. One was physical chemistry, which I was working with but the applications there was always, we had Josef Kovalevsky, who was the head of the division, and at the time also head of the department. He was doing basically relaxation in small molecules and paramagnetic systems. Then we had other groups that were specialized in MD simulations, but pretty much nobody was doing work on inorganic materials, as opposed to actually the rest of the department, the divisions of inorganic chemistry and structural chemistry. So when I got back to Stockholm, I had some collaborations with people working on oxynitrides, including oxynitride glasses, which actually turned out there was also another assistant professor, Said Esmail Sadeh. He basically discovered, more or less by accident, that oxynitride silicate-based glasses, they have enormous mechanical properties. So that was basically the spin-off of, I would say, multi-million or multi-tens of millions dollars industry, so to say, or company. So I basically wanted to switch to inorganic materials, because at the time that was really what most of the department was doing, except for the people in physical chemistry.
You have a series of articles on dissolution behavior of bioactive glasses. silicate, phosphosilicate bioactive glasses for heart tissue regeneration. I think around 2011, something like that. You started, I think, working on these type of glasses and studying the dissolution behavior and using NMR to understand the mechanism of glass dissolution and all these things. It's interesting. It's about 40 years after the invention of 45s5 bioactive glass. So at the time, I mean, when you wanted to do this project, this working on bioactive glasses, what was the understanding of the structure of the glass and the relationship between the structure of the glass and the dissolution property? I think you've done a great job. It's very comprehensive, and using NMR easily, not easily, but readily you can link the glass structure to the dissolution behavior. So what was the understanding at the time? Wasn't it surprising for you that it's not systematically been studied very well?
Okay, let's maybe start for the audience to explain a little bit what bioactive glasses are, and that's something that you actually find in toothpaste. Like you said, they were discovered in the very early 70s. I think they are about as old as I am myself, and the idea, they were discovered by Larry Hench, and the idea basically then was to, instead of using metals that are very foreign to the body and sooner or later will always be expelled, the idea was basically to use materials that naturally integrated with the body tissue. So then he invented bioactive glasses, which basically they are fairly poor mechanical properties, although that is also something that has been an intensive area of research over the past 2 decades or so. But they're really great, let's say, for filling holes in bone and tooth. And bioactive glass itself, I think, has been in the so-called 45s5 glass has been in clinical use, I think, now for probably, I suspect, since the 80s even. So the idea basically is that these are silicate-based glasses. You very often add phosphorus to improve the kind of bone bonding properties, which basically bioactivity you can basically equate to bone bonding properties or how efficient they are. So what happens when these glasses then get in contact with body fluid is that there will be some surface reactions, and that is what you refer to, what we partially were studying. And eventually that leads to basically deposition of calcium phosphate, initially amorphous, but which transforms into basically the mineral calcium hydroxyapatite, which you find in natural, it's a natural mineral. And it turns out also that hydroxyapatite is really close to the bone mineral itself, so that somehow naturally explains why it may easily form or bond to the tissues. It can also bond to soft tissues. It's not only hard. So at the time, I think that, to get back to your question concerning what was known, it's now probably almost 10 years ago since I stopped working in this area, so I actually forgotten quite a bit. But from what I understand, most of the work back then to study basically how efficient the glass dissolves if you're doing it under in vitro condition. You're using something which they call a simulated body fluid, which basically is mimicking all the inorganic constituents of body fluids, blood, and but it doesn't have any biological molecules. So you basically then expose the glass. You can do it either with glass monoliths, which was done traditionally. Later on, people have also started using just glass powders. And I think there has been a lot of studies. I think that most of them focused on the composition dependence somehow, and there were formulations of about, let's say, about something like more than 60 mole percent silica or something. Don't hold me to the exact number, but above a certain amount of silica, the glass becomes not reactive really. Then people have noticed, which is known back since Larry Hensch, I suspect that they did a lot of studies and had data that was probably never published. But what we were trying to do was to do a more sort of rational design. I mean, we were for sure not the only ones sort of working along those lines. But what we tried to do basically was to first apply NMR and then try to understand what the results were telling us, and then draw conclusions about how you possibly can somehow later on design better glasses. That was at least the aim. So we had a long-standing collaboration with the group of Maria Vallet Reggi in Madrid. They were providing us the materials, and these glasses I should say, they were actually mesoporous materials. They are called mesoporous bioactive glasses. So strictly speaking, they are not glasses but mesoporous materials. What connects to the glass is that the pore walls in these materials are basically amorphous. So we were studying by phosphorus NMR, we were looking into the formation of this amorphous calcium phosphate, which is basically, amorphous tricalcium phosphate, if you simplify it. And this then converts into better ordered apatite. So by phosphorus NMR, I think we were actually first. It's a quite simple, straightforward experiment, but I think we were the first to do it, to basically monitor for increasing exposure times in vitro, how the apatite was formed, and basically to quantify it as fractions of amorphous calcium phosphate and the ordered hydroxyapatite. So we could monitor the sort of end stages. And when I say stages, what we basically ended up pretty much confirming was another of all the contributions Hensch did to this field. He basically had formulated, you can say it's like a 5-stage reaction sequence from when the bioactive glass is exposed to the body fluid to the end when you have apatite. And it basically starts by a series of surface reaction at the silica. And here silicon-29 NMR, single pulse to get quantitative information, but also cross-polarization, since you can do a surface selective probing of the surface, because these materials will not contain any protons inside the pore walls, but at the pore walls, when they are exposed to the solution, you have, of course, water molecules, but also a lot of silanol groups. That is basically silicon with 1 or 2 OH groups.
Mm-hmm.
So we were doing silicon-29 NMR there to study that. And what we ended up with basically was pretty much more or less to confirm that the mechanism by Hensch was pretty much working. And then later on, I continued doing NMR and study more or less the melt quench bioactive glasses. And one of the things that we really learned from there was that the conditions, your in vitro conditions, when you do this testing, will be very dependent on basically the amount of the powder you have in relation to the solution. That has somehow been known, but there were not so much standardized procedures. Later on, I think during the early 2000s, there were an ISO standardized procedure for doing SPF testing. But the point with that is that one is also actually quite incomplete. So one of the things we learned, and which I think I have in 2 papers, but it has never actually been really recognized by people or cited or mentioned, is that one of the well, big take-home messages is that what you have to ensure when you're doing this testing is that you have to really look at the composition of your bioactive glass. And then you have it exposed in a solution which contains calcium and phosphate, which also the glass contains. You have to make sure that you have much more phosphorus and calcium available in the solution than what the glass material has itself. Because otherwise, what will typically happen is that people have known for quite a while that if you add phosphorus, you usually get somehow better bioactivity. But a lot of that is coming from the glass. And in a real environment with a flowing blood in your body, it's probably not going to matter that much that you have it. But you have at least when you're doing the in vitro testing to ensure that you have a larger amount to form the apatite already available in the solution so that everything is not just coming from your glass. If it does, or a majority does, you can actually get quite misleading results. And we learned it the hard way, I can say.
Okay, interesting. So you said that the findings that is interesting for you, they didn't get attention from the community in the glass or in the bioactive or biomaterial community. So what's the reason for I don't want to say not being recognized, maybe not being delivered to the community? So you put so much time and effort on doing something, and when you publish it, you think that the job is done, right? But I think the other thing is to deliver it to the proper audience. Is it a challenge for you as a professor?
I would say both yes and no. In general, not. If you take this concrete example, it's one example of many times that we put it into a paper which has, we basically very rarely, if ever, publish 1 point per paper, so to say. So usually our papers are too long. In this particular context, like I said, it was basically published twice, but it was still like a minor part of a larger paper. If you would have split it up and published it separately, then probably it could have gained better recognition. And that might be a general problem with our papers, that we basically try to make them as complete as possible from the beginning. And something that I also learned over years, which earlier would feel totally foreign to me, is that you probably have to basically duplicate and restate things over and over until they are got. I mean, I think there are many such examples. And that's something that I somehow, from my background and how I was somehow trained to do science, it somehow that was rather along the lines that you should sort of avoid somehow recycling things. Now I start to realize over time that you somehow have to do it, because not everybody will see that particular paper, and particularly not like in our case, which very long papers which are really multiple points, so to say.
Yeah, that was another question I wanted to ask. I've seen some of your articles. They are quite long, complex, and so do you do it intentionally? I mean, the long, should I say, not hard to read. Maybe the concept is by itself, it's complex. So is there any reason behind it to write? I have, I think, one of the examples I can pull it up and talk about it, but it's quite long and different types of NMR, and I think it's on glass science and very complex. So is there any reason to do that, or my knowledge is limited? I don't understand it, so it doesn't mean that it's complex. I should learn more.
Well, I think it has to do with many things. First of all, is the problem with the long papers. I mean, that's something I think that has grown out, like I explained a little bit how I've been trained to do research and so on. And then in some cases we have split up papers, but very often that leads to other problems. So usually I try to make it as complete as possible. The price you pay is going to be a long paper. And you can find also some of the senior, let's say the groups NMR on glasses, like Helmut Eckert, for instance, they also publish very long papers. So we are not alone, but the problem with it is then also how it's delivered. So my aim has always been, since my early sort of years in research, is try to do things to deliver things with clarity. The problem becomes when these papers get long, because then I do what I can to really condense the language. It's still going to say the same thing, but it's going to take more efforts to read, and we have a combination of having a notation which is probably very different from, at least if you take, let's say, glass science. Now I'm not only working in glass science, but I think that this is a combination of my background in physical chemistry and also coming from a field totally outside of the glass sort of glass community, is that we tend to have a quite complex notation, which if you understand it, you will see that it actually is very helpful because you can quickly somehow understand things. But the mistake I'm probably doing is that I take for granted that people understand the logics behind it. And I can mention that because that's something that just struck me a few years ago. If I look back when I, for instance, was taking, let's say, courses in, let's say, quantum mechanics and so on, very often I realized that some of the things I had things I struggled with. One of the really very major things that I learned from Malcolm, which was really helpful. Well, it's basically, I would say, many things, but the two main was to how to deliver presentations, but also somehow how to make notation. That we tend to use a lot of sub and superscripts, and nowadays it feels like a symbol without any of those. It feels a bit naked, so to say. But the whole idea is then calling things A, B, C, and X, Y, Z, or some Greek letters, which you all the time need to look back. What was this symbol? You use a unifying symbol, and then so as soon as you see the symbol, you will see, for instance, this is a fraction. We denote, in my group, we always denote everything with fractions as an X, and then like a subscript telling what fraction. And in that case, you don't need to remember A, B, and C, what fractions they represented. And when I was looking back in one of the books, I think it was by, let me see, what is the name of, he's written so many books. Yeah, Atkins. I was looking at it, and I could immediately see that if the notation would have been a little bit more logical, maybe more complex if you think that sub and superscripts are complex. But if it would be more logical, I would have easier understood it. And so I think that it's a matter of, the problem is that I write our papers. I'm trying to basically start with a sort of pedagogical approach to, I mean, if you look at most of the introductions, I'm actually giving a few sentences just how a silicate glass is built, which you normally don't find in most papers because it's assumed that it's known. I'm trying to deliver that, but then there are some other issues concerning complex notation, long papers, and so on, which probably makes the papers not so approachable for people who have not somehow a more solid background in, let's say, structures and so on, or mathematics for that matter.
Yeah, I wanted to say that I have seen that you have your own style and formatting and convention, nomenclature, I would say, when it comes to glass science. For example, N4, I've seen that you, N4, the ratio of, in a bored system, in a bored glass, we have 3-coordinate and 4-coordinate boron, and people in the community, researchers, usually they say N4, the fraction of 4-coordinated boron that we calculate from the integrated intensity of boron NMR, different fittings. And I think you have you don't use this convention. Again, if I read an article without knowing that you have written it, I mean, if I just don't look at the names, I can understand that this is from Mattias Edén. So
I'm quite determined not to use jargon language and to use a notation that somehow as accurately describes what it is. So what we are using is probably, instead of the N4, which is one of the notations, I think they were probably introduced by Bray or maybe even somebody earlier in him. This is a notation you find for now probably easily more than 70 years, and nobody has done anything about it. What I don't like about it is that N, capital N, to me, that represents a number. So if I would refer to the number of a four-coordinated boron, I would probably use N. But as you said, it's not a number, it's a fractional population.
yeah,
And then what we are using instead is a small x, because everything which contains x should be taken, it's going to be a fraction. And then the superscript with brackets 4 says that it's the for coordination, and the subscript B tells that it's for boron. So it's a complex notation, but once you understand that, if you see the X3B or XAL4, you can also easily realize what they refer to. If you take aluminium, for instance, there is not a common convention with, let's say, saying N4 there or N5, for instance, for 5-coordinated aluminium.
okay.
But we're using basically a consistent notation which will work for any kind of element and coordination, and without needing then to introduce, we anyway introduce the symbols, but once we have introduced one of them, if you understand that, you can quite easily pick up what would be meant in a, I would say, totally different context.
Yeah. So I want to change a little bit the topic to a more general question that let's say that you are doing a project using different techniques. You're primarily working with NMR, and then you use other techniques like FTIR, Raman, to get more results, let's say, to confirm your the logic or the reasoning using other techniques. What if you get conflicting results from Raman and NMR? What's your approach to explain it? Do you use both of them and you say, this is what we got, or you just use the one that you are more confident and more comfortable with?
Okay, to give a quick answer to the question, I would say that I am critical to everything which we do. I'm also critical to what others do. You can probably see that also from our papers, that we I tend to be quite critical. Sometimes I also praise things, but I am critical. So concerning the NMR, I would say that if it really would come down to a matter of NMR and IR, there would be seeming inconsistencies. I would usually rather trust the NMR, but I would be very sure that that is really justified also. But to put things a little bit sort of more generally, which is basically a major component of our research now since probably 15 years or so, is that even if NMR has been our core technique, over a long time now, our equally core technique is molecular dynamic simulations. I've been working with Balsa Stevenson now for pretty much 20 years. He has been working part-time for me over all this time, and he has been responsible for all the modeling in the group. I would say that if there is one thing that has the possibility to really boost and simplify the research, is to have molecular dynamics simulations available, because you can get far by NMR. The problem is with glasses is that you can get a few, maybe very fancy information, but you never get the full picture. If you have MD simulations available, you can really benefit from that. And I would say that that's probably the single most important thing if I look how my research has developed, from starting with only NMR, then also starting to exploit MD simulations. Besides that, you get information which you can never get by NMR. It actually also helps you to identify and analyze your NMR experiments. So the way we usually work is that we first validate the MD simulation results against experimental ones. And once we see we have a good agreement, and actually we usually find a good agreement, then we go on using mainly the MD simulations to derive all of these other results. And I would say that I found this tremendously important. So if the question then would be, what do you trust between NMR and MD simulations? I would say that in general, naturally, I will trust the experiments, but there are cases where actually I've been in cases where actually the MD simulations appear actually to be probably more trustable than the NMR results.
Interesting. So I have another question about how the research interest a PhD student have affect your research activity. I mean, let's say you get a student interested in doing glass science, digging into the structure of the glass, or another one would love to develop NMR pulse sequences. So how do they affect the research that you are doing? How do they affect your priority in doing research in your group?
I think that most of our projects, and if I'm looking at the PhD students I had, they usually are more interested in the systems than the NMR itself. But then I also had, let's say, like René Matthew, who did, he's in Dubai right now, but he did PhD for me, but he also worked for 2 years later as a postdoc in two not continuous sections. I mean, he was really great and understood. He's coming from somehow an NMR background from the beginning. All his projects, he was working on bioactive glasses and also later on basically bioactive phosphate cements, where we basically used advanced NMR. And to some extent, he also had his own somehow ideas there how to do. So I think looking at the people working in my group over the years, they have some, let's say, postdocs that come to learn NMR, which have all the chances to do. But mostly people have been interested more in the applied things. And I think that is one nice thing with the glass research and what we're doing is that we use NMR, we use MD simulations, even though actually my students or postdocs are never involved in those particularly, but they somehow, since we work closely with Baltzar, we also have that part, including also, let's say, some of, the bioactive glasses. Initially, all the in vitro testing was done in Spain. When we later ourselves continued with melt prepared glasses, then I had another PhD student, Yang Yu, who was very productive, who did all of that. So I think that the mixture between things have somehow always sorted out in a way that I think that the people involved has been interested in all aspects, I would say. I hope at least.
Yeah. So I want to move beyond the lab, but before, I have another question. I think it's interesting. Have you published an article and other researchers in the community found it controversial?
Not to my knowledge have we published anything that has somehow been heavily criticized. It might be controversial rather in the sense that, like I said, and which is also very obvious from many papers, that we tend to be quite critical. And a reason for that, I would say, is to not to be nasty, but to basically first clarify this is what was stated, this is what we state, and why we think it's somehow better. I think it's from the scientific viewpoint, I think it's a much more transparent way than, let's say, if you don't like something and you will anyway come up with something totally different. I think it's better to actually comment that rather than to totally pretend like nothing and just ignore it.
Yeah.
So I could imagine that some people feel that they are stepped on the toes. That I could imagine. But if you're talking about controversial of our own results, not to my knowledge. Like I said, on the other hand, there has been some papers which I think has been really useful and important, which has basically been ignored. But I would say those are rather exceptions to the rules rather than.
So, like the bioactive glass that you mentioned, one of them maybe. Okay. So let's move to beyond the lab, and I'd like to ask a few questions about the personal aspects of your life. So what do you do in your spare time?
I used to work for many years, pretty much. I had very little spare time. Now I'm still probably doing more than 40 hours per week of work, but I'm working half of what I used to do. So in my spare time, I like to watch movies. That I've been doing for many decades. Then I also have a little bit newer hobby, which also connects to my chemistry interest. When I was younger, I was also interested, well, at chemistry, you know that when you're a kid, poisons are interesting. So I was interested in poisonous plants. And I've been growing, well, I have basically my living room, lots of plants, poisonous nightshades in particular, also other like plants for medical use. Like, I don't know if you know belladonna,
No.
datura, henbane. They are in the group of nightshades, which you actually also find a lot of your food. Potatoes, peppers, and eggplants are also nightshades. But these are contain atropine and scopolamine. They have been some of these dates back to basically, witches and so on. It's they are poisonous, and at lower dose they are basically also hallucinogenic.
What I mean, how do you take care of them? You have a specific gloves, maybe. If you touch them,
No, that's not an issue. It's not so. I think belladonna has, I think, been referred to as the most poisonous plant on the northern hemisphere, but it's not like you cannot touch them. That's not an issue. They are
okay.
not that. And they have been for medical use a lot. Let's say scopolamine, for instance, you have in medicine. When you if you're exposed to rotations. I mean, if you're sitting in a car, some people get sick, or like, let's say, seasick. This is scopolamine is basically something that I think is still a medication against that. But at higher doses, scopolamine is also. I'm also growing this so-called brugmansia. I'm not sure if that's the English word, which you find in South America, which basically are used to rob people, because you get basically very submissive when you get scopolamine.
That's interesting. So, have you tested them?
No, not really. No, they are. I mean, the problem with this, I mean, if you look on the net, let's say for datura, you can find probably a lot of kids who have tried it. Many of them end up at hospital. It's basically horror trips.
Oh.
And what is also very dangerous with them is that the gap between to have, let's say, hallucinogenic effects and also dying is very close. So they are extremely dangerous in that sense.
Okay. So, what was your dream job when you were a kid?
one of the things which I always liked is to write. So I think when I was a kid, I wanted to become an author. I mean, not for scientific literature, but for let's say novels and so on. So I always liked writing, and that's something also, in this type of profession, which you're doing a lot.
Yeah.
Unfortunately, I think that I used to write much better Swedish 20 years ago, because everything I do now, I'm even thinking in English. So I become very, but I wanted to be an author. I got a typewriter by my parents when I think I was around 10. So I used to write a lot.
Okay. In an imaginary world, in another parallel world, what's your job?
Oh, I still think I would be a scientist, maybe not doing what I'm doing now. Alternatively, journalist along the lines of writing. Unfortunately, I'm very bad at handling stress. Otherwise, journalist would be something I would really like as a profession.
That's interesting. So, do you have any regret in your professional life, or
Well, not really overall. The difference is that like I said, I used to work pretty much 24/7. That's something that I regret. It wears you out over time, and I've noticed that. I don't have the same energy, nearly the same energy as I had 20 years ago.
so if a time machine existed, would you rather go 100 years back or forward?
If it only would be for one time, I think it would be interesting to knowing how the world looks at 100 years. But if I had the choice, I would really also, maybe not 100 years. If I'm looking how it was in Sweden then, I still think we probably have it better then. But I think it would be very cool to go back, let's say in the very early 70s when I was born. I mean, the first few years as a kid, you don't remember so much, but it would be that I think would be cool. Go back, let's say 50 years ago.
Yeah, that's interesting. And your favorite scientist in the history?
Oh, if you're talking chemistry, I would probably say Carl Scheele, who you probably never heard of. But he discovered many elements, including oxygen and nitrogen, which is pretty cool. The only problem, he did it independently, but he wasn't the first to do it. Oxygen, I guess it was Priestley. But he was a pharmacist during the 1800th century, and he actually did a lot of he discovered a lot of things, including organic acids and, like I said, oxygen, nitrogen, also barium, and I think and molybdenum. So I would say, he's not that well known. I mean, Sweden has several very well known chemists, not the least Arrhenius. If you're asking about overall, I would say probably Galilei was the ultra master of pretty much everything. Concerning physics, probably all of these old guys inventing or not inventing, but developing quantum mechanics like Niels Bohr, Heisenberg, and Schrödinger.
Okay, interesting. Is there anything that you wanted to say I didn't ask?
No, not really. I think your questions has been very good and also personalized. So
Yeah,
appreciate that.
yeah. Thank you for your time, and uh, enjoy your evening. We have a time difference, and
You too, and have a nice weekend.
yeah. Thank you. Bye.
Thank you. Bye.